Good day. In this video, we will be reporting about the theory of special and general relativity. Furthermore, we will also be discussing about the consequences of the postulates of special relativity, the way special relativity resolved the conflict between Newtonian mechanics and Maxwell's electromagnetic theory, and the predictions of general relativity. And for our reporters today, we will have me, Kirby, Bendijo, Lance Marquez, Shekinah Peñaranda, Magno, and lastly, Jasmine, Llado. Good day everyone. In this segment of the video, I will be defining and explaining one of the most fundamental theories in physics. This theory was formed by renowned scientist Albert Einstein, and it is called Einstein's theory of special relativity. So let's start. First, let's define what the theory is. Einstein's theory of special relativity is a scientific theory proposed by Albert Einstein in 1905. It basically describes how the laws of physics operate in a system that is moving relative to an observer. Furthermore, Einstein's theory of special relativity is based on two postulates. First one being the relativity postulate and the speed of light postulate. With the first postulate stating that the laws of physics are the same for all observers moving at a constant velocity, regardless of their relative motion. This would mean that there is no absolute reference frame for measuring motion. For the second postulate, it states that the speed of light is constant in all reference frames. This means that the speed of light is the same for all observers, regardless of their relative motion. So, to better understand this all, imagine that you're sitting on a train that is moving at a constant speed. To you, everything in the train looks normal. You can walk around, eat, play games, just like you would if you were sitting still. But to someone watching outside the train, things will start to look a little different. They might see the train moving past them at a fast speed, and to them, it would seem like time on the train is moving slower than time outside the train. So, to put things simply, the faster you're moving, the slower time appears to be passing for you. And if you're watching someone else who's moving fast, it will start to look like their time is going slower too. So now, let us head over to the consequences of the postulates of special relativity.
Let's discuss the consequences of the postulates of special relativity. First is time dilation. Time appears to move slower for objects moving very quickly to a stationary object according to special relativity. This means that if you were traveling at nearly the speed of light in a spaceship, time would appear to slow down for you in comparison to someone who is stationary. Next is length contraction. A further consequence of special relativity is that for an observer who is stationary relative to the object appears shorter in the direction of their motion. This means that if you were traveling at nearly the speed of light in a spaceship, objects in the direction you are moving would appear shorter than if you were stationary. Next is the relativistic mass increase. The mass of an object appears to increase as it approaches the speed of light. This means that it takes more and more energy to accelerate an object, and reaching the speed of light becomes increasingly difficult. Mass-energy equivalent. According to Einstein, mass and energy are two forms of the same thing. This means that a small amount of mass can be converted into a large amount of energy as demonstrated by nuclear reactions. According to special relativity, there is no such thing as absolute rest. This means that in the universe, there is no preferred state of motion and all motion is relative. In other words, regardless of direction or speed, the laws of physics apply to all observers moving at a constant speed relative to each other. Lastly, special relativity shows us that space and time are not absolutes but are intertwined and dependent on the observer's frame of reference. This means that the way we experience space and time depends on how we are moving through the universe.
Now, let us focus more on the concept introduced in Einstein's special relativity, which is no other than space-time. Space-time is the fabric of the universe that contains everything we see and experience. It is made up of three dimensions of space, which is length, width, and height, and one dimension of time, which are past, present, or future, making it part of a four-dimensional continuum. Now, according to Einstein's theory of relativity, the fabric of space-time is not static, but it can be warped, stretched, and distorted by the presence of matter and energy. So the more matter and energy there is in a region of space, the more it warps the space-time around it. This new framework allowed for the unification of the laws of physics, including the Newtonian mechanics and also Maxwell's electromagnetic theory. To recall, Newtonian mechanics explains how objects move when acted upon by forces such as gravity, friction, or a push or pull. It also explains how objects interact with each other, such as in collisions or when one object exerts a force on another. On the other hand, besides telling that the value of the speed of light is constant, Maxwell's electromagnetic theory also explains how electromagnetic waves propagate through space, including light, radio waves, and X-rays. Now, how does Einstein's special relativity fit into this? As it tells the speed of light being constant in all frames of reference, it introduces the principle of relativity, which is the idea of the speed of light being constant. The principle of relativity is the idea that all physical laws should be the same for all observers who are moving with a constant velocity relative to each other. This means that there is no preferred frame of reference in the universe. The laws of physics should work the same way for someone standing still on Earth as they would for someone traveling at a constant speed in a spaceship, for example. In other words, the laws of physics are independent of the observer's motion, and the same basic principles apply no matter how fast you are moving. This principle is a cornerstone of modern physics and has led to many important discoveries and advancements in our understanding of the universe.
The theory of general relativity is a crucial principle of physics that explains the behavior of gravity and its impact on the structures of space and time. It is based on the idea that regardless of their movement, all observers should encounter equivalent laws of physics. It has significantly altered our comprehension of space, time, and gravity, revolutionizing our perception of the universe. In addition to what was discussed last week, black holes are another proof supporting this theory's prediction. The nature of gravity and matter conduct in extreme conditions were clarified by it, which determines on energy and matter distribution, calculated through Einstein's field of equations, when objects with enormous masses like stars become so intensely curved that they form a black hole with an event horizon marking the point beyond which there is no return in spacetime. Another piece of evidence to propose this theory is the universe expansion. As per this theory, how matter and energy are distributed in space should determine how space-time curves and whether the universe will expand or contract. Edwin Hubble, an astronomer from the early 20th century, observed that distant galaxies seemed to be moving away from the Earth. He noted that as they got farther away, they moved even faster. This observation suggested that the universe was expanding and provided strong evidence for what general relativity predicted. And because of Einstein's equations, scientists came up with the Big Bang theory, which describes how the entire universe came into being and evolved. Additionally, it predicts that due to dark energy, there should be an acceleration in how fast our universe expands. This prediction has been confirmed because the observations of distant supernovae lead us towards new insights about matter and energy on a much larger scale.
Scientists use theories to make predictions which can then be tested through experiments or observations. According to my research, general relativity is a theory that describes how gravity affects the structure of space-time, and it has made many predictions that have been confirmed through experiments supporting the theory. And here are several predictions that come from the general relativity. First, time dilation. It is a prediction that comes from general relativity, which talks about how gravity affects space and time. It proposes that time moves differently in places with different amounts of gravity. Suppose an astronaut is in a spaceship orbiting a planet. The planet's strong gravitational pull causes time to pass slower for the astronaut than for the people on Earth. This means that if the astronaut came back to Earth, they would have aged less than someone who had remained on Earth for the same duration. This means that time isn't fixed and can change based on where you are or how fast you're moving. Second is the frame dragging, also known as the lens steering effect. It is when the rotation of a massive object causes a distortion in the surrounding space and time, dragging it along with it in a twisting effect. This can be compared to stirring honey with a spoon, where the movement of the spoon creates a swirling flow in the liquid. There have been several experiments and observations, like NASA's Gravity Probe B mission launched in 2004, that have indirectly confirmed this phenomenon. Third is the gravitational redshift. It describes the stretching of light waves that pass through a gravitational field. Also, when light travels away from a big object, it loses some of its energy. This makes its color change slightly and its wavelength becomes longer. This change can help scientists figure out how much mass or weight the object has. They can also use this information to design better tools and technology that can work in areas with strong gravity. Lastly, the cosmological constant is a form of energy that exists throughout space. It produces negative pressure, opposing the force of gravity, and results in the accelerated expansion of the universe. This concept has significance for the structure and ultimate fate of the universe, as well as the behavior of energy and matter on a cosmic scale. Suppose a rocket that is moving into space by burning fuel to create energy and thrust. Similarly, the expansion of the universe is powered by the energy produced by the cosmological constant. With the generation of more energy, the universe's expansion accelerates, similar to how a rocket accelerates as it burns more fuel. As our understanding of general relativity continues to evolve, we will likely make even more groundbreaking discoveries about the fundamental nature of space, time, and the universe as a whole.